I hope you all got a lot of sleep and weren't up all night thinking about nuclei. Marek, do you have any announcements?
No.
Okay. So let's get started. First of all, the slides that were up on the website last night, I'm going to replace them, Pete will replace them, with a completely new set that includes the NNDC slides, and which includes the exercises with the answers. Okay, and I thought I would spend some minutes here first going through the exercises and talking about them and the answers a little. Is it okay to reveal the answers? Okay. Okay, ready? Good. So this is a table or a slide I showed from NNDC yesterday, and I had a mistake here. I just wanted to correct it. This is I gamma E2 over the total I gamma is delta over 1 plus delta squared. I had that wrong yesterday. Okay. Okay, so here was the first question, and in red are the answers. So in this case, you have two levels 100 kilovolts apart with a small interaction. And you see that the levels only move about a kilovolt. And the beta, the small component of the mixing amplitude, is 0.1. I mean, beta squared is 1%. Here you have the same initial separation, but a large matrix element. And now this 200 kilovolt level moves 62 kilovolts. And the mixing amplitude, I mean, it's almost completely mixed, or at least it's very large mixing. Here I have 500 kilovolts and 25 keV interaction. That's not so different than the first one, but I just wanted to kind of show you that things scale. And then the upper level moves a little over a kilovolt, and the mixing amplitude is quite small. So those, I actually wanted you to do by hand. Hand to me means actually with one of these things that you write with. Have you seen those? They're called pens. They don't have little buttons. Some of you couldn't resist using Excel, but anyway, I was hoping you'd do them by hand because you actually learned something by seeing the numbers fly by. In any case, I think you all got these in the end. Here are two degenerate levels with a 10 kilovolt mixing matrix element, and so the first level moves up 10 and one goes down 10, and the mixing is complete. It's as mixed as they can get. And here, same two initial levels, 100 kilovolt interaction. Now that one moves up 100 and one moves down 100, and same mixing. And what I wanted you to notice here, in addition to the energies, here I say in D and E, what do you notice about the wave functions? Notice the wave functions don't change. Now, in every other case, if you have non-degenerate levels, and you mix them, and you change the interaction strength by an order of magnitude, the wave functions will change tremendously. But not for the case of degenerate levels. That will turn out to be important in the third week when we discuss, for example, the IBA model and the idea of symmetries. And then here, 5 degenerate levels, all at 1,000 kilovolts, all mixing with each other with interactions of 100 kilovolts. So one level goes down to 600, 4 go up to 1,100, and all the wave functions are constant. What does that mean? Oh, I asked for the wave function of the lowest state. It's just all amplitudes with 1 over the square root of 5. All amplitudes equal. Okay, that was pretty simple, but since it was the first exercise, it took a while to get into things. Now here, I asked you to diagonalize. Oh, by the way, see the word negative? Some of you missed it because it was in red. I should have said here negative as well, so sorry about that. Anyway, here I gave you some levels which are not degenerate and some sort of random matrix elements which are fairly large. And I asked you to diagonalize it with Mathematica, and I think in the end just about everybody got connected with Mathematica. Maybe one or two of you still had problems. Here's the input. Here's the output. And there's several things to notice. Remember, the input energies were 500, 600, 700, 800, 900. Let's start here. The 900 moves up. The 800 moves up, the 700 moves up, the 600 moves up. the 500 moves way down. Okay, so one level again is lowered substantially, the others are raised. And look at the wave functions. This is the wave function of the lowest state. You'll notice, first of all, that the signs of all the amplitudes are the same. And you notice they range over a factor of about 4, from 0.8 to 3.1. Look at the other ones. For example, this one. The amplitudes range over 2 orders of magnitude, from 1 to 169, and you have a mixture of signs. So it's a feature of the degenerate case that one state goes down and is lowered, and all the amplitudes are in phase and all equal. The others are all raised. This is not a degenerate case, and it's not all equal matrix elements. It's more realistic, okay? But you still get the same basic qualitative feature. One level is lowered, the others are raised, and the lowered one has a coherent wave function with all the amplitudes in phase. Okay? All right. I asked you to compare the independent particle model predictions for the first 4 states with antimony 133 and terbium 169. Now, if you remember the comments, some of you were puzzled by this because the antimony didn't work exactly. You got the rights, 3 of the 4 states had spins and parities that were consistent with the experiment, but the order wasn't right. And if you remember when I showed you the independent particle model diagram of levels with the magic numbers, I said, don't believe these. I mean, don't take them as coming from the mountaintop. They're a snapshot for a given mass, and they will change with mass. As the radius of the nucleus changes, high and low angular momentum orbits are affected differently. Lots of things can happen, Coulomb effects and so on. So these are snapshots for a given mass region, and the one I showed you might have been calculated, I don't remember where I got it, it might have been calculated for some mass 50 or something instead of mass 133, and so the order of these levels can change. Okay, they generally won't go from one major shell to another, but within a shell you can get shifts. So don't be too shocked if you see that. So some of you actually used a different diagram, which you liked better, and which actually worked better. It was probably more tuned to that mass region. Okay, for 169YB, this was, in a sense, a trick question. The answers you would get just using the independent particle model by taking the 70 protons here and just assuming they all pair to 0 because of the residual interaction. And this has 99 neutrons, taking 98 of them and pairing them off. And then you have one last neutron, and looking in the shell model diagram and seeing what orbit it falls into and then putting it up into successive orbits. You get this. You could get slightly different versions depending on how you do it. They have nothing to do with the data. The data doesn't look like that at all. And so some of you realize that this would probably happen since this is mid-shell in protons and mid-shell in neutrons. And so you don't expect this model to work, and I wanted you to see that it didn't work. And in the 3rd week, we'll discuss a model called the Nielsen model, and you'll see how simple it is to understand something like that. Okay. Now I asked you to look up the ERAS levels in NNDC for these nuclei and to comment on their structure. I specifically asked you to look only at the ERAS levels because with the models we discussed yesterday, that's all we talked about. Some of you knew about other things and tried to fold that in, which is fine, but I wanted you to sort of take you step by step. So for cadmium-112, if you look at the 4:2 energy ratio, it's about 2.3. And so most of you correctly said, well, it's close to a vibrator, but not quite. The vibrator, if you remember, has 2.0. It turns out experimentally that nearly all nuclei that we usually associate with vibrational structure don't have R42s of 2.0, but have R42s of typically 2.2 to 2.3. This is about as good a vibrational nucleus as you can get. There is even currently dispute in the literature about whether it really is or not, but it looks pretty good if you look at all the data, I think, but that's my opinion. Okay. 164 dysprosium had an R42 value of about 3.29 or something, and some of you said it's a perfect rotor. Well, it's a good rotor. It's not a perfect rotor, because perfect would be 3.33, and we will see where those small differences can be important later. 152 samarium has an R42 value of 3.01, and so you said it's transitional. Most of you got that right, which is good. 190 osmium I put in here. This, again, is kind of a trick question. It has an R42 value of, 2.87? I can't remember. Anyway, and you said it was transitional. You will see today that there's more to it than that, and you have to look at non-ERAS levels to see that. 238 uranium was simple. For these two nuclei, I think the 4:2 ratio in one of them is not even known, and so I put the comment here. This actually wasn't in the question itself, but I said it verbally. R42, if you only have the ERAS levels, R42 is very useful. But in some cases, it's better to look at E2 plus alone. And if you made a plot of E2 plus for silicon and for magnesium as a function of neutron number, you saw a big jump for silicon at n equals 20. And big jumps in E2 plus are symptomatic of magic nuclei. And no jump at all in magnesium. And so what I wanted you to see here was that the magic numbers can change. Okie dokie. All right, so here, now I've changed the question from the one you saw yesterday because we were running out of time, and so I said to simplify it. The question you saw yesterday asked you to do look at the decay in erbium-168 for all the gamma band states, but then I said just do it for the 2 plus gamma and also ignore uncertainties. We will come back to this today, and you will be tortured by having to do some more work on that. And I asked you to normalize this transition to 100 and to make a table. And the table is coming up. Here is the table. So the 2 to 2 is normalized to 100. The 2 to 0 is 56.2. The 2 to 4 is 7.3. And I think in the end, more or less, all of you got that. There were some steps along the way where you got different numbers, like 2042. Or something else, but in the end, it was just numerical mistakes. The key here was just getting a little bit familiar with this e to the 5th factor. Okay, now, you'll notice this table sort of cuts off here and is kind of short. In one of the exercises today, I'm going to ask you to fill this out for the 3 plus, the 4 plus, the 5 plus, and the 6 plus. And for the 3 plus and 5 plus, to come up with these uncertainties as well. Calculating the uncertainties is a little bit of a pain in the neck, but it's very important for both experimentalists and theorists. If you're going to compare with the data, you've got to know how accurate the data are. And there will be another column out here that I'll ask you to fill in. We'll discuss that topic today. Okay, now I asked you which theory is better.
When we have a ratio and we normalize something, how do we calculate the error?
Okay, good question. So there are two different ways. If you look at the intensity of this in the nuclear data sheets, it has an uncertainty of 2%.
Yeah, it also has a certain.
Yeah, so you could put 2% there, 2 on the last digit, and put the uncertainties for each of these. What most people do is to fix this at 100 and combine those two errors into here and into here, just in quadrature. Okay, it's a little, huh?
Which one is right?
I don't think either is right, but if you talk about normalizing 1 to 100, it's nice to think of it as having that value. I don't think there's a right and, I don't think there's a right and wrong. This is the way I do it. It's the way I think most people do it, but I've seen the other as well. Okay? Okay, so I asked you which theory is better. Now, I'm not sure all of you got to this. Who actually got to do this? Raise your hands. Okay. Who didn't get to do it? Who didn't raise their hand for either answer? Okay. You guys study some rules, don't you? Okay, so let's actually do this here. So, which theory is better, theory 1 or theory 2? And I'm not going to embarrass you. You can all close your eyes and just raise your hands. Who thinks theory 1 is better? Who thinks theory 2 is better? Who doesn't think? I didn't see every hand up. I want to see all hands up. Who thinks theory 1 is better? Who thinks theory 2 is better? I noticed your hand wasn't up. Okay. All right. Why do you think theory 2 is better? Yeah. No, wait a minute. You did it yesterday. So the people who did it, I don't want to answer. Why do you think theory 2 is better?
Because the electricity experimental does pretty well in these structures.
Okay. All right. Let's look at chi-squared. So let's calculate the difference between the experimental and the theoretical values divided by the experimental error. And what do you get? You get that chi-squared for theory 1 is 2 times 10 to the 4th, and chi-squared for theory 2 is 10 to the 6th. Now, let's vote again. Who thinks theory 1 is better? Who thinks theory 2 is better? Who heard me say that theory 2 is better yesterday? Okay. So why? What's going on? What's the message here? There are actually a couple of messages. This is a very important point because all of you, whether you're theorists or experimentalists, are going to be comparing data with theory, or you're going to be doing theory so exotic that there's no data ever possible on it. But let's hope that you're here because you're going to do something practical. So you'll notice here that this experimental energy is accurate to 1 electron volt. And so is this. And these are accurate to 2 kilovolts. Now, first of all, that's not impossible. There are experimental techniques that do this. It's fairly straightforward, although uncommon, to measure gamma ray energies to an electron volt. And perhaps these states were not seen by gamma ray spectroscopy, but by particle spectroscopy. So you could easily get this. What you have here in theory 2, by the way, theory 2 is better. What you have is nearly perfect agreement, but 1 kilovolt off. But when you take into account that this is 1 electron volt uncertainty, the chi-squared is just absolutely dominated by that. That's a factor of 1,000, which when you square it is 10 to the 6th. Okay? What's missing is the idea of theoretical uncertainties. You need to, whenever you make a comparison of experiment and theory, you need to fold in the idea of how accurate you expect the theory to be. Now, we could get into a long discussion of how you know how accurate theories can be, but we won't. But in any case, somehow you have to estimate or take into account somehow what you expect for the theory. Okay? And if the theory if you say the theory should be accurate, let's say to 10 kilovolts, then using 1 electron volt here is just going to misguide you completely. So here I do an example where I take 10 kilovolts for all the levels, okay, and I write the errors like this, and then I get new chi-squareds, 800 and 0.01. And that much better reflects the actual quality of these two calculations. So the message here is take theoretical uncertainties into account. And you can fight for days and weeks about what value to put in here, but at some level you have to put in something. And if you don't, you'll make wrong conclusions. And so one message here is don't let super precise data bias your model testing. Now, that's not a message not to measure things precisely. Okay, it's great to measure things precisely, but don't let an accidentally precise value like this completely dominate the comparisons. Okay? All right. So this example had to do with what you do when faced with precise data and the idea of introducing theoretical uncertainties. And for this example, I'm just putting in 10 kilovolts for everything. Now, here's another example. Which theory is the worst? So who thinks theory 1 is the worst? Who thinks theory 2 is the worst? Who thinks theory 3 is the worst? Who knows that I think theory 1 is the worst? Who's not being honest? Okay. Why do you think theory 1 is the worst? They're all the same chi-squared. Each one misses a level by 100 kilovolts. No, 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 you did them. You did them. Somebody who didn't, did you do them yesterday? Okay.
I would just guess, one, since you want your theory to hit the lower lying excited states more, because being off by 100 there is like a 100% error, whereas being off by 100 when your value is 1300 is like a 10% error.
Who agrees with that? Everybody disagrees with, oh, who agrees with that? Who disagrees with it? So all the other hands should go up. Okay, why do you disagree?
Well, I think I won't be honest because we discussed.
Okay, then don't say anything. Okay.
I mean, we discussed.
Yeah, okay, but I want people who haven't discussed it. Did we discuss? Did we discuss?
No.
Okay.
I think Justin made a good point about.
Which one is Justin? I haven't memorized all the names yet.
But in this case, we've been studying the E42 value, and that is what we use to characterize the rotational vibrational modes. So having the 4 state be off by 100 kilovolts is going to mischaracterize.
Okay. You're both right. I don't think, so to get this wrong is really means the entire theory is getting the nucleus wrong. It's saying it's something like a vibrator. It's not exactly a proportionality to the energy. It's not the fact that, whoops. It's not the fact that these are 4 times, how long was that stuff up there? Was it up there all the time? Okay, okay. It's not just the fact that these energies are 4 times higher. It's that these are, you can see this is a rotational nucleus. These are simply rotational excitation energies, and a theory should be able to get those to within a few kilovolts. And to miss the structure completely means the theory is just absolutely wrong. These two get that level perfectly. One is off by 1 and one's off by 100 here. I'm not going to go into which one of these two is better. I personally think this one is, but if not, we don't need to discuss that. Okay, so here you have what I just said. Theory 1 misses the structure completely. And the message here is you need to put some physics insight into evaluating models. You can't just go blindly and look at chi-squareds. Well, here it wouldn't help. Or just say, well, they're all equal. And there's another message. So this is what I just said. The theory should get the ERAST energies to within a few kilovolts. It's really easy. Lots of models will give you that. And you're generally happy with these vibrational energies if you're within about 100 kilovolts. If you put those theoretical uncertainties in, you get 1001. Okay? There's a message here which may not be, I mean, it's the important message is that theoretical uncertainties are observable dependent. So in the previous slide, we took 10 kilovolts flat out for all the theoretical uncertainties. Here, we have one theoretical uncertainty for the ERAS levels, namely 3 kilovolts, and another for here, 100. So the theoretical uncertainties depend on what observable you're looking at. Now, it's not so easy to have a rigorous formula for how to do this. A lot is based on experience and so on, but it's something you always need to take into account. Okay, so that is good. That's what I wanted to do on that. And so this set of slides with the NNDC and with those exercises will go up on the website. Okay, so now this is today's lecture. This is just the next to last slide I showed yesterday. Did I correct it there? Yes. And I showed this one and made the comment about the e to the 5th factor killing the low energy gamma rays. And also experimentally you have the problem these low energy gamma rays are on a high background. The message there was be careful. If you're doing an experiment, don't say you're happy with the amount of statistics when you have big peaks out here. Look there. In fact, one of the most, I guess, important experiments I ever did was, and I actually didn't do it, Peter Brentano and a student in Cologne did it, was to measure one of these beta decay spectrum for 3 or 4 weeks. Now, I think they left a source in front of the detector and went on vacation, but he claims they did it intentionally. Anyway, the point of it was they got infinitely good statistics and found the non-existence of a gamma ray there because the statistics were so good, and that was really key to a model. Okay, so always look down here at the low energy transitions, which are the hardest to see, and pay attention to those. Okay, so now today, click to add title. I forgot. Okay, so far we've dealt with cases of a few nucleons in a single J orbit. And we talked about residual interactions affecting the energies of those levels. What happens when we start filling proton and neutron shells with more and more particles? Okay, so first let's talk about configurations. So if we have a set of nucleons, protons or neutrons, that can fill certain orbits, question we immediately have to... Oh, sorry. Thank you. Did anyone see that number? No, don't. Okay, configurations. So let's say we have a set of nucleons that can occupy certain orbits. Once you have more than one nucleon, you have to ask what angular momenta they can couple to. We talked about that already yesterday with the M scheme in a simple case. And you know for that if I have 2 particles in H9 halves, they can couple to 0, 2, 4, 6, or 8, right? You could all do the M scheme and tell me that. Okay. Notice that there's only one configuration of each J value. Okay? There's only one 0 plus state, only one 2, only one 4, and so on. So what are the effects of the residual interactions? They can shift the energies. We saw that yesterday. But they can't mix any wave functions because you can only mix states of the same angular momentum. And so there's no mixing that occurs here. Let's take another example. 2 neutrons that we allow to occupy either... Oh, I'm sorry. I edited this part later and forgot to change that. I'll do that before we put it up. H9 halves or D5 halves. Okay, this should be D5 halves. Okay, so for positive parity, we can have 2 configurations. We can have H9 halves squared, in which case we get J equals 0, 2, 4, 6, 8. Or we could have D5 halves squared, where we get 0, 2, 4. Okie dokie? All right. So now you'll notice there are 2 ways of making a 0 plus state, 2 ways of making a 2 plus state, 2 ways of making a 4 plus state, and 1 each for 6 and 8. So if we have a residual interaction, it can mix the configurations of the 0, 2, and 4. So that's a non-diagonal effect of residual interactions in addition to any energy shifts. Okay? And so that becomes important once you allow particles to occupy multiple orbits. Okay, now I want to go through an exercise, and I want to ask you a question. Down here, when the slides raced through, there was a number in a box. Did any of you see that number? Are you being honest? Good. Okay, good. Okay, so as you increase the number of valence nucleons, the number of ways of making a given state grows very rapidly. And I want to go through a couple of cases. So let's consider 2 particles in a D5 halves orbit. How many ways can you make a 2 plus state? Don't be influenced by the answer. There's one way, right? They can couple to 0, 2, or 4. What about if you have 4 particles that can occupy a D5 halves or G7 halves state? Now, I didn't do this very carefully. I don't know the exact number, but I wrote down 7 ways you could do it. There might be more. You could have 2 particles in D5 halves coupling to angular momentum 2, and the other in G7 halves coupling to angular momentum 0. Can you all see this, by the way, back in the back? Okay. You could have 2 particles in D5 halves coupled to angular momentum 0, 2 particles in G7 halves coupling to angular momentum 2. You could have two particles in d5 halves coupling to angular momentum 4, and two particles in g7 halves coupling to angular momentum 2, and then couple the 4 and the 2 to 2, going like this. You could have two particles in d5 halves coupled to 2, two particles in g7 halves coupled to 4, couple that to 2, and so on and so forth. Okay? And I wrote down 7 ways. I don't know if there are more. Okay? So here we have 4 particles in 2 orbits. We can make at least 7 configurations. So if you have a residual interaction, these 7 configurations will mix to greater or lesser extent depending on the interaction. The wave functions will begin to develop some kind of correlations in collectivity. These 7 configurations will not all be at the same energy. It will take a different amount of energy to put 2 particles in d5 halves as it would in g7 halves, or to have 2 particles in d5 halves and 2 particles in g7 halves. So these initial levels will not be degenerate. And some of them will mix and some won't mix depending on the residual interaction, excuse me. So this is a little like that second Mathematica matrix, or the Mathematica matrix you had to do. They're not degenerate levels, they're not all equal interactions, but you will still begin to develop this correlated collective state where one state tends to come down low, other states do something else. Okay? Now, here's a question. Suppose this is a very famous example. I didn't do it. 154 samarium. It has 62 protons and 92 neutrons. The nearest closed shells are 50 and 82, so it has 12 valence protons and 10 valence neutrons. The valence protons will allow to fill this 50 to 82 shell. The valence neutrons, the 82 to 126. And the question is, how many 2 plus states can we make subject to the Pauli principle? Okay, and I want you to guess. So if you know the answer, a few of you know the answer. Mallory, you probably know the answer, right? We must have discussed this. I know Riley knows the answer. So you're not allowed to say. And anybody, you may know the answer. So, Okay, so if you know the answer, don't say it. But I'd like you to make an estimate of what you think the answer is. Be careful what you say. What do you...
No, the first time you asked this, I made totally wrong estimate.
Okay, good. I hope all of you are as wrong as he is. Okay, so somebody say something. How many 2 plus states? I'm going to point to somebody in a minute. So somebody say something.
10 to the power 4.
10 to the power 4. 10,000?
I don't know.
Okay, good answer. Some other answer? What did you guess? Or you were just commenting on his?
Yeah, well, 10 up to 10.
Sorry? 10? Okay. Another answer? Come on. You can't be... Just give an answer. Yes? 0. Okay. Yeah. The answer is 1 in arbitrary units, yes. In units in which H bar and C and everything else is 1, it's 1. Okay, some more answers. Do you want to answer? Sorry? Way more than 10 to the 4th. Okay, this side of the room is getting very aggressive. So what do you think over here? The worst you can be is wrong.
That's really big.
You also use hundreds?
Hundreds. Hundreds?
Yeah.
Okay. Somewhere in the back. Oh, over here in the back.
Count, just say 10 to the something power, and then someone will be right. I will just start from 2,
Well, I
1, 4,
Sorry?
4.
He's calculating.
10 to 12. 10 to 10. Really big number.
10 to the 10th.
10 to 12, yeah.
10 to 12.
Yeah.
Okay.
So many
So
So we have numbers ranging from 0 to 10 to the 12. Okay. Should we just take the average? Okay, come on. I want 1 or 2 more answers. Something over here.
10 to the 6.
who said that? 10 to the 6th, okay. And one from over in this region. You can't be more wrong than some of the answers already. You. What?
10,000.
10,000. He said that already, so you agree with him. Okay. All right. Now, I was worried that I would accidentally click this, so I put in a buffer. All right, here's the answer. 3 times 10 to the 14th. Okay?
If you combine the 10 over the n by 4, then it's perfect.
Yeah, if you take the product of yours. Okay. So that's a lot. Okay, so for an exercise, I'm going to ask you to diagonalize a 3 times 10 to the 14th matrix. Okay, the point is, we can't deal with this, at least not yet. Actually, shell model diagonalization or diagonalization routines using some special techniques can now get up to what, 10 to the 11th, I guess?
10 billion.
That's 10 to the 10th, but I think they can get even a little higher, maybe only in Spain. But in any case, let's imagine you could diagonalize this. And let's say I asked you to, so you did that, and I asked you to look at the wave function components and tell me the structure. Well, first of all, if I asked you to print out the wave function, there'd be no trees left in France. Okay, if I asked you to look at it, you'd be looking at 10 to the 14th components. It would be very hard to see anything simple. I'm not saying that's not a good thing to do. I'm just saying it's not a way to give you an intuitive feel for what's going on. So you need to do something else. And what we're going to talk about today are what some of these other things are. Okay.
How you get this number?
I didn't. I found it out from Igal Talmi, who did it using group theory. And Pete could probably explain.
I will give tomorrow an estimate. It's not exactly this. I mean, to get exactly the 2 pluses, that is difficult. But to have the number in the M scheme, that's not so hard. So I will give the formula.
The real number, by the way, is 2.89 and then some other digits. It's known exactly. But so I got it just because someone told me. Okay? Okay, so how can we calculate this? Well, there are lots of microscopic techniques, shell model, ab initio calculations, Monte Carlo methods, all sorts of things that are making amazing progress in recent years. It's really been a tremendous success. And I just picked up one that I happen to have. These are some calculations using a potential developed at Argonne. And this is really an amazing amount of progress. However, you notice it only goes up to carbon-12. And so for the foreseeable future, it's limited to pretty light nuclei. Okay, if you want to go and study zirconium or cadmium or uranium or whatever, you have to do something else, at least for the moment. And so that's where collective models come in. And they bypass this idea of all the nucleonic interactions. This is the macroscopic approach I talked about in my very first slide. They look at the many-body system as a whole with a shape, a structure, quantum number, symmetry, selection rules, and so on. And that's what we're going to discuss the rest of today. Okay. When there are multiple states with the same J, we know that they can mix with each other due to residual interactions. We don't know a priori what the individual unperturbed energies are. We don't know what the mixing matrix elements are. But from basic quantum mechanics, we know the general effect. Namely, that it'll tend to produce a low-line collective state, or more than one, with wave functions that are coherent. And the larger the number of states that can mix, the larger n is, okay, the more the collectivity will grow. Now, if you go back to that 3 times 10 to the 14th number, and if you imagine that all those 10 to the 14th states are degenerate, and if you imagine the residual interaction mixes all of them equally, okay? You remember the calculation we did very early yesterday with the BE2? And we said the BE2 from the 2 plus to the 0 plus came out as n times any one of those. That would give us a BE2 3 times 10 to the 14th times what any one of the individual transitions would be. Experimentally, those numbers are about 200. Okay, so 200 and 10 to the 14th are quite different. And so a simple picture like this really can't, it's really a toy model. But it does contain the essence of the physics, which is what I hoped you would see with that little mathematical diagonalization yesterday. So this is an extreme picture. But the general characteristics persist. One state comes down in energy. It tends to be collective. It has enhanced transition rates. And so here I have a cartoon of how structure varies from magic to magic. You start off with this kind of 2-valence nucleon system where you have a high 2 plus and other close line levels. R42 is less than 2. You add some valence nucleons, you go through a vibrational regime where R42 is on the order of 2. You get to mid-shell and you get rotational spectra. And these arrows are the BE2s, and the thickness is proportional to the value. And so the thickness grows. And then once you pass mid-shell, you always count these valence nucleons to the nearest closed shell, whether it's above or below. So you kind of reverse the picture. It doesn't reverse absolutely symmetrically in real nuclei, but this gives you the idea of how it goes. And this is observed experimentally. Okay, so 2 plus energy comes down, R4-2 ratio goes up, the BE2 values increase. Very characteristic of shell evolution everywhere. Okay, so now how can we understand this? There are two basic approaches. One is geometrical models, which introduce a potential that depends on the shape of the nucleus. This is a different potential than the one we talked about yesterday for individual nucleons. That was a potential that depended on the radius of the particle from the center. This is going to be a potential that depends on the shape of the nucleus. And algebraic models, which invoke symmetries of the nucleus and use group theory and so on, I will discuss these today in, is Jean talking in the second week or third?
Second week.
So in the second week and then again in the third. Will there be anything on algebraic models this week?
Yes, I will give on Thursday.
For fermions or
In general.
in general? Okay. So you will hear a lot about algebraic models in these 3 weeks, including from me in the third week again, with some practical calculations. But today I want to focus on geometric models. Okay, and there are two. Each one has little brothers and sisters that are related to it and offshoots and so on. But the basic types are these two. So we'll start with a vibrator. And I showed this slide yesterday. If you have a spherical nucleus which is not absolutely rigid, but has some softness to it so it can oscillate back and forth, you can get a quadrupole excitation with 2 units of angular momentum. And having an integer spin, it's a phonon. It satisfies both Fermi statistics. And we'll see what that means in a minute. And whoops, maybe we'll see it sooner than I thought. I thought there was something else coming. Anyway, it will come. You can have more than one of these phonons. And as you saw yesterday, or at least as we said, you could make a 4 plus state. Okay? But if you take 2 phonons with angular momentum 2, you might be able to make other angular momenta. Imagine you take a 2 plus angular momentum phonon like this and another one like this. You could make a 0. Maybe you could make other things. So the first thing we have to do is find out if you have more than one phonon, what angular momenta you can make. And we use the M scheme. But now we're using the M scheme for bosons, not for fermions. So the Pauli principle enters in a very different way. So let's go through this. This is for 2 bosons, 2 phonons, each with angular momentum 2. And so we again make this little table. Let's say that the first one can occupy magnetic substate 2. Okay? The second one can also occupy magnetic substate 2. They're bosons, not fermions. That gives you a total magnetic quantum number of 4. You can also have 2 and 1, which gives you 3, 2 and 0, which gives you 2, 2 and minus 1 gives you 1, 2 and minus 2 gives you 0. Then you have to drop this. You can go to 1. 1 and 1 gives 2. 1 and 2 you can't do because you've got it there already. 1 and 0, 1 and minus 1, 0 and 0, and symmetric for the negative values, which I just don't bother to write. Okay? And now you look at this, and, well, you tell me, what can you say about the angular momentum states you can make? If you know the answer, I mean, I want you to get it from the table, not from knowing the answer. Yes? How did you do that so quickly? Okay, so, all right, so you looked at the whole table. I want to just go a little step by step. You see the maximum magnetic substate is 4. So there has to be a spin 4 state. That spin 4 state has to have magnetic quantum numbers 3 and so on. There's no other 3. So you can't have another spin 3. So the next highest is 2. And as you said, you get 4, 2, and 0. Okay? So those are the 3 states you can make. It's an interesting thing. Remember we did like H9 halves squared with fermions? Or let's say D5 halves squared with fermions. What would you get? 0, 2, 4. Same thing. Funny, huh? Okay. Anyway, so you can make 3 states. And we'll see what happens if you have 3 phonons in a minute. And this afternoon, you'll find out what happens if you have 4 phonons. Okay, so that means we can make 3 states, a 0, a 2, a 4, at twice the energy, because you need 2 of these phonons, as the 1 phonon state. And so this is the kind of spectrum you would expect. Okay? I want to introduce creation and destruction operators. Do you all know about these? Is there anybody who has not encountered these? Okay, so I'll go very quickly through this then. So what are these funny things called creation and destruction operators? Basically, they're ignorance operators. When you don't know the structure of a state, you can still learn a lot of things about it by using these operators as, as creating and destroying the state as a whole without knowing the detailed microscopic nature of it. Okay, with the dagger, it's a creation operator. Without the dagger, it's a destruction operator. I'm going to drop these subscripts because we're only talking about quadruple ones. The basic rules are the following. I think, Pete, will you derive these?
There will be an exercise.
Okay, so there'll be an exercise. So you guys will derive them. Okay, so a destruction operator acting on a state with n sub b phonons of type B gives you a state with 1 fewer phonon, because it destroys 1, and some number, square root of NB. Creation operator acting on that same state gives you a state with 1 more phonon and another square root. Okay? Okay. An interesting quantity is this product operator, B dagger B. And let's look at what that does. So let's operate on a state with NB phonons with B dagger B. So just keep the B dagger over there and do B. So B acting on this will give you this formula, n sub B, n minus 1. Okay? This is just a number, so we can pull it out. And then B dagger operating on NB minus 1 will give you NB back, and it'll give you this square root. I'm just using this formula, but starting with NB minus 1. Okay, the square root of NB minus 1 plus 1 is square root of NB. So this gives you square root of NB times square root of NB times wave function NB, which gives you NB times what you started with.
So you just did my exercise.
Forget you saw this. I thought you were going to have them derive these results.
Also, yes.
Okay, well, all right, so I'm sorry. Okay, so it counts the number of phonons. I'm sorry, Pete. I showed you my slides before this. You obviously didn't look at them. Okay, so we can derive some interesting things from this. Let's look at this little scheme where we have 1 phonon, 2 phonons, 0, 2, 0, 2, 4. Okay, suppose I have a destruction operator acting between states with Ni initial and Ni final. If you go through this exercise, which is trivial now for you, you get the square root of Ni times a delta function, which is only non-zero if NF final is Ni minus 1. Okay? So this kind of matrix element only changes the number of phonons by 1 and reduces them. Okay? the transition probability, so this would correspond to a transition from an a state with Ni phonons to one with NF phonons, and it will only happen if the number of phonons in the final state is one less than the number in the initial state. The transition probability, the BE2, will be proportional to the square of this matrix element. So the BE2 value is proportional to the number of phonons in the initial state. Okay, so now we can already make a prediction. If I define this BE2 value to be 1, then this will clearly be 2. Okay? If you want a physical reason why this works, here you have two phonons and you have two choices. You can choose to destroy either one. So you have twice the probability of doing it. Okay, so that's one prediction of this vibrator model, that these BE2 values should be twice these. You have the selection rule we've already talked about, that you can only change the number of phonons by 1. You have a branching ratio, which we've already discussed, namely this over this is 2. And you have the result that transitions from this 2-phonon state to the ground state, which change the number of phonons by 2, are forbidden. Okay, so some very simple predictions of this model. Okay, now, what happens if we have, I will show later, actually I'm going to add in a slide during the break, which I meant to add in, showing you how this works in a real case a little better, which I meant to do this morning, but I forgot. What happens with 3 phonons? Okay. Anybody want to do the M scheme in their head? I mean, here are the final magnetic substates. So what spins do we have? If you know the answer, don't just say it. I mean, get it from the table. What's the highest spin you can make? 6. Okay. What's the next highest?
4.
Next highest?
4.
Okay, you can make 6. So 6 has to use up magnetic quantum numbers from 6 down to 0. So 6, 5, 4, 3, 2, and I've got to pick up a 1 and a 0 somewhere here.
2, 1.
Sorry?
6, 4, 3, 2, 0.
How did you do that so quickly? Okay, you didn't know the result.
No, sir.
Okay. Okay. So the answer is 6, 4, 3, 2, 0. 5 states, known as the 3-phonon quintuplet. Okay? So these are the 5 states you can make. Okay? Here is a level scheme for cadmium-110 experimentally. Okay? And remember, no nucleus is ever going to look exactly like these idealized models. Okay, but here's cadmium-110. You have a ground state, naturally. You have a 2+ state at about 600 kilovolts. You have a set of 4, 2, and 0 at an energy about, let's see, this is 658 kilovolts. That's 1547, so it's a little more than 2 to 1. It's about 2.2 or so to 1. A nearby 2+. 0+ is pushed up somehow, okay? And it's typical that the levels are not, these should be degenerate in the pure model. It's typical that they're not, but these are relatively close together. They're within 200-300 kilovolts, which is half of the phonon spacing. Okay? Then you have a set of states which look like a 3-phonon state. Just one sec, okay? 6, 4, 3, 2, 0. You have a set of phonons which are, a set of states which look like 4-phonon, 5-phonon, so on. When this was first developed, it was considered shocking because, and I'm not going to go into this, but if you think about the microscopic, I talk about these as vibrations, but you also have to always think of what's going on at the nucleon level. And these vibrations correspond to exciting nucleons from one orbit to another. Now imagine that you're going to put a particle from a d5 orbit into an s1/2 orbit. Just imagine that that's a major part of one of these vibrations. Well, once I've done it twice, I've filled that s1/2 orbit. I can't do it a third time. So people didn't expect these 3, 4, and 5 phonon states to exist. And then level schemes like this were found, and it was pretty shocking. And the BE2 values, and that's the slide I'm going to add in, the BE2 values are not terrible. They're not perfect at all. And there's still a lot of controversy about whether these are really good vibrational nuclei. There's at least one group that claims not, so That's truth in advertising. My own opinion is yes, but okay, there's disputes. But what you see are these beautiful multiplets that look like phonon states. Yes?
So I was just wondering because the spectra is very, the level scheme is very equidistant, and when you analyze data and look at the spectra, these spectra will have like a bunch of lines just bunch to each other.
Yeah.
Doesn't this make it a little bit hard to analyze?
So you're asking an experimental question, right, about the spectra. You're saying that this transition, this, and this, they'll all be roughly the same energy, and so the peaks may overlap.
Yeah.
Yeah. If you use germanium detectors, which have, say, 2 kilovolts,
Yeah.
well, let's say tenth of a kilovolt precision and 2 or 3, let's say 3 kilovolts resolution, generally speaking, you're okay. Okay. You can also use a technique.
No, okay, but people before that, like which year was this discovered?
Oh,
Was it the 50s?
15, 20 years ago, the 90s. No, these higher phonon states only in the 90s.
So because people didn't have good germaniums.
No, germanium detectors came in the late 60s. In fact, the very first thing I ever did in physics was to build germanium detectors. Take a piece of germanium and make a detector out of it. I did that with a guy named Joe Allen. Has anybody ever heard of Joe Allen? No. Sic transit gloria. Okay, he did a thesis at Yale on light nuclei, SD shell, silicon, sulfur, looking at deformation and so on. And then he left the field and became an astronaut. And he went around the Earth hundreds and hundreds of times. And on the second moon landing, he was the person in Houston who was the communicator. So many of us our age have actually heard his voice without probably knowing it. Okay, anyway, that's off the topic. Germanium detectors have been around for a long time. And you're pretty much okay. You can also use technique of coincidences. You can, I'll get a little technical here for you. You can gate on a transition like this, and then you won't see the 6 to 2, you won't, okay? So you can do gating, various gating techniques to simplify the spectra. You can do multiple gates. So you can sort it out. And if you do the experiment at a place like the ELL in Grenoble, they have detectors that are called crystal spectrometers, which work by diffraction. And they can get these energies to an electron volt. Okay? Yes?
So it seems you can predict the even spacings, but is there any way to predict what this effective frequency of vibration is?
Oh, you mean the absolute scale?
Right, like being able to predict omega naught here.
Yeah, no. Well, I don't mean no. Of course not. I mean, there's a difference between a collective model and a microscopic model. A microscopic model meaning nucleons and their interactions. Collective models, almost invariably, you cannot predict the scale. Okay, you have to put that in. Okay, with microscopic models, the scale should come out. If you do, okay, I'll do techno talk for a second. If you do an RPA calculation, for example, you should be able to get the energy of the phonon state. Okay? All right. Well, at some level of accuracy. And the better the theory, the better you can do it. So, also, you should be able to get these non-degeneracies. Okay? All right. Other questions? All questions have been good so far because there's no such thing as a stupid question.
Well, I was wondering if there's maybe some nice intersection of light to medium nuclei where you can kind of hit them both from an ab initio and collective perspective. And
okay, so I was about to nod yes. When you said ab initio, there you got a little bit of a problem. Let's talk about microscopic, which could be large basis shell model calculations, where you still take a core. Maybe you take a nickel 68 core or something like that. And yes, in that region, roughly mass 60 to 100, people are doing large basis shell model calculations nowadays and getting, I think, reasonable results. Would you agree?
Yes, but like this example would be very hard in the shell model, for instance.
Because of the orbits involved.
Yes.
Yeah, yeah. But like for example, in the zinc isotopes, that region, those are simpler. I think the answer is yes. You have a comment? Okay. Okay? Okay. So this is a real spectrum of a nucleus that seems to look quite a bit like a vibrator. And I will put in a table of the BE2s because I think it's worthwhile seeing them because it gives you another feeling for how good or bad these idealized models are. Okay. Now, gamma ray transitions. This is, I mean, seeing the energy levels is one thing, but you always want to look at transition rates. They're very sensitive. Remember, the selection rule is you can create or destroy a single phonon. And so these transitions are allowed, but that one is forbidden. And so one of the obvious things you would do is you'd look at the ratio of this gamma ray intensity to this, correct for the e to the fifth factor, and see what the ratio of BE2 values is. Okay, I want to... I want to make a comment about these three phonon states now. There's an interesting facet of these, which may not be obvious at first. Let's take a three phonon state of angular momentum 2. You can make it three different ways. You can couple two phonons to 0, and then use the third to make 2 plus angular momentum, like this. You can take two, well, I'll do this one. You can take two and couple them to 4, and then anti-align the third one to make angular momentum 2. Or you can couple two of them to 2 and then couple the third to make angular momentum 2. These are three independent ways of making a three phonon state. Now imagine a transition, an E2 transition from a three phonon state to a two phonon state. You can destroy the third phonon in any of these cases. And so by the way, speaking of lawnmowers, I knew I was going to be in Europe for 6 weeks, so I went to the barber and asked him to cut my hair short. My hair doesn't normally look like this. He went crazy. Okay. Anyway, so you can destroy any one of these phonons, which means this 2 plus state can decay to a 0 plus state by destroying this phonon. It can decay to a 2 plus state by destroying this, or to a 4 plus state by destroying this. Okay? And so we can end up with all of these. Somebody remind me to put an E there. Okay, and this is what you get. And I know you're going to do this, right, Pete? With your CFPs?
I will discuss it.
Okay, all right. So remember, if this is 1 unit of transition strength, these transitions from the 2 phonon state are 2. The transitions from the 3 phonon state should be 3. And so here you see the 6 plus, which decays with 3 units of BE2 value to the 4 plus. The 2 plus can go to the 0, the 2, and the 4 with these relative BE2 values. Now, I'm not deriving these. I'm just telling you. If you add up these, you get 49 plus 20. They're all over 35. 49 plus 20 is 69, plus 36 is 105. 105 divided by 35 is also 3. So in this case, the sum of the 3 BE2 values gives you 3. These particular ratios can be derived with a technique called coefficients of fractional parentage, which Pete will talk about tomorrow. Okay. And so what you would look for in the experimental spectra are not only 3 transitions from this level to these 3, but with relative BE2 values taking on those numbers. Okay? Okay. Oh, I took out a slide. Okay. I wanted to show you another one. It doesn't matter. There are some other examples where... let me comment on these selection rules.
And one remark if you go back. These states are not independent. Huh?
No, but there are 3... There are 3 independent ways of making them.
Of making the
Yeah.
steady state.
Yeah. Okay. All right. Sorry. You're right. So I wanted to show a nucleus here, which I, for some reason, deleted the slide. It's cadmium-118, which shows these relative BE2 values and shows that the ratio of the forbidden ones to the allowed ones is on the order of 20. Oh, well, 1 over 20. So the forbidden ones are a few percent of the allowed ones, which means that at that's the level at which the model works. It's predicting that it predicts that the forbidden ones are 0, and in fact they're 3 to 10% of the allowed ones. And that's relatively good agreement. And that's, by the way, if you do any kind of analysis of a spectrum and compare with theory, when you talk about theoretical uncertainties, you have to fold that kind of idea in. Okay, now I want to talk about deformed nuclei. So I'm making a big switch in topic here. What time is it, by the way? Oh, okay, we got plenty of time. Okay, so now I'm switching to deformed nuclei. So I've covered what I want to on spherical nuclei. Are there any questions on those? Is your hand up or you? No. Okay. Well, you are sort of like this. Okay. Any questions? Tins to ask. Okay. Is it clear so far? Did someone say no? Huh? No, it's clear. Okay. Okay. It's okay. Am I going too fast? Am I going too fast? Am I going too slow? Oh.
Why is it that in real life this model is not perfect?
These models are so extremely simplified. For one thing, I actually gave you a reason already. If you think about making these phonons microscopically in terms of particles, okay? Let's take the simple model I talked about. Let's say you have particles, the ground state has the d5 halves orbit filled. And let's say there's an s1/2 orbit up here. And let's make a trivial example where making a phonon takes a particle from d5 halves to s1/2. That will have angular momentum 2, or could. Okay? And now let's say I make a 2-phonon model. That means I superpose 2 of these. So I take 2 particles out of d5 halves and put them into s1/2. Now let's say I make a 3-phonon model. I take 3 particles out of d5 halves and I put them into s1/2. I can't do it. s1/2 is filled. So the 3-phonon state has to have a modified wave function. Now that component of the phonon, d5 halves to s1/2, may only be 10% of the phonon. There will be other components. But that part will have to change. And so the structure of the phonon as you go up in the spectrum will be modified. Okay? The amazing thing is that it works at all. Okay?
So shouldn't the angular momentum of the phonon, which, you know, we're treating them like bosons, we're just going from 0 to 2 to 4, wouldn't it be determined by the single particle angular momentum that we're pushing the particle through?
I would say it the other way. If you want to have a quadrupole phonon spectrum, that limits which particle excitations you can have in it. They all have to have angular momentum 2.
Okay.
So you have to change the angular momentum by 2. That you could go from s1/2 to d5 halves. You could also go g7 halves to g9 halves because they can couple to 2.
So depending on where you are, this conservation of angular momentum could really determine the energy jump of this single.
Sure, absolutely. Absolutely. So here's something to think about while I'm talking. Think about the collectivity of these states depends on the number of different ways you can make that angular momentum. Okay, and it's more collective, lower line, the more ways you can make it. Think about the collectivity of octopole vibrations. Now don't get distracted while we're talking, but just put that in the back of your mind. Okay. Don't lose the rest of the stuff for that. Okay. Okay, is that clear? I mean, I'm not discussing the microscopic structure of these phonons, but you have to always realize there is a microscopic structure. The microscopic model and these collective models are not incompatible. They're just different ways of looking at the same thing, and they have to be compatible in the end. Okay? To me, the amazing thing is they work at all. It's like the joke where the guy who went into the bar with a dog, and he said to the bartender that this dog is amazing, he can talk. And the bartender said, "Wow, come on." And he asked the dog, "What's 2 plus 2?" And the dog says, 5. And the guy says, the dog is stupid. And so the owner says, no, the amazing thing is he can talk at all. Okay, so the amazing thing is that these models work at all. They are so simple. Okay, and I'll make this point later when we talk about oligo rules. Yes?
The angular momentum of a fauna is equal to 2. Is our definition or is it derived from some...
No, we're trying to understand states which have these angular momentum 2 characters. Okay, you could also do it with angular momentum 3. You could have octupole phonons. Okay, now for reasons that, don't tell me. Winston? No. Did I get it?
No.
But I'm close.
Yeah.
It's two syllables.
Two syllables. The last syllable's relatively quick.
So what was it?
Justin.
Justin, okay. Winston, Justin, okay. In first order, that's the same. Okay, so he's actually thinking about this while we talk. So you can have other kinds. You can have hexadecapole with angular momentum 4. But there are reasons why these are not very common. And we'll talk about that later. Okay, that's a good question. Okay? All right, so, whoops. So now deformed ellipsoidal nuclei. Okay, nuclei can have non-spherical shapes. And I'm not going to get very formal about this, but I just need to introduce these two variables. So here's an ellipsoidal nucleus. And this axis is longer than this. And that elongation, that deformation, is usually parameterized in terms of a quantity called beta. You'll often see beta, people will say the deformation is beta is 0 point whatever the value. Okay? There are, by the way, in the literature, other notations for this. There's epsilon, there's delta, there's even eta. You guys probably will never encounter eta, but in the past it was used. They're all, if you see an epsilon or a delta or a beta, they're all the same within about 5%. They're slightly different definitions. Most people use beta. And then there's another parameter, or not parameter, but variable, called gamma, which is the axial asymmetry. And what I try to illustrate here is, I colored this yellow because I'm looking end on now. And the nucleus, if this is the first one on the left, okay, if I squeeze it like this, then that's axially asymmetric. And that angular dependence in this way is specified by gamma. Okay, so, and you have a radius now, which is not just a single quantity as you would have for a sphere, but depends on beta and gamma. Okay? Now, obviously, you can make a model of a nuclei like this in a geometrical sense by having a model which has a potential which is expressed in terms of beta and gamma. And we will look at that very briefly toward the end of the morning if I get to it. Okay? And it'll have some interesting aspects to the discussion. Okay, so I want to collect a bunch of things here. So first of all, if we have a deformed nucleus, and I look at the change in radius relative to the sphere of the same volume in the z direction, which is always the elongation direction, the y direction and the x direction, these are the formulas from the previous slide. Okay, and here I collect some numbers. So gamma equals 0. No, oh, by the way, there are different conventions for gamma. Gamma equals 0 is always an axially symmetric prolate American football type nucleus. The shapes for these other gammas, they're different conventions. Okay, I'm using a convention where 0 is prolate, 60 is oblate, and 30 is the most axially asymmetric. Okay, so for gamma equals 0, delta RZ is plus 1 in units of these square roots, and delta Rx and delta Ry are equal and half as much. So what that means is you take a sphere, you elongate it in this direction. To conserve volume, you squeeze it in this direction and squeeze it in this direction. Okay? If you go to 30 degrees, then all three directions are different. And so that's axially asymmetric. Okay, that means that you have, well, I think it's clear. Okay. If you go to 60 degrees, whoops. If you go to 60 degrees, RZ and RX are equal and positive, and RY is the opposite sign. So an oblate nucleus, so this is a prolate, oh, here's a better prolate nucleus. This is a prolate nucleus. An oblate nucleus is shaped like a disc, like a frisbee, okay? And if you think about getting from a sphere to a frisbee, you have to elongate it in two directions and squeeze it in one. For a prolate, you have to elongate it in one and squeeze it in two. So that's the difference between prolate and oblate. Namely, in a prolate nucleus, prolate, you elongate it in one direction, squeeze it in two. Oblate, you elongate it in two directions to make a disc, and you squeeze it in one. Okay, so that gives you some feeling for the shapes. Okay. Moment of inertia. We've already encountered the moment of inertia when we talked about rotational formulas. Remember the energies went as h bar squared over 2I times jj plus 1? So here's I. Now, you all know what the classic moment of inertia for an object is. It's mr squared, the sum over infinitesimal elements of mr squared, or for a rod, it's mr squared. Mr squared. R squared is the distance squared. M is the mass. Okay? For a nucleus, the mass is the number of nucleons times the mass, and that goes as the radius. So the moment of inertia goes as a to the 5/3. Okay? Here's 3/3, and r is a to the 1/3, so r squared is 2/3, so it goes as a to the 5/3. Okay? That means as the mass of the nucleus increases, the moment of inertia will increase. It depends on beta. Where's beta? 1 plus 0.31 beta. And this has an important implication for looking at data. We talked about R42, and this is one of the reasons why it's so useful. An R42 of less than 2, you immediately know something about the nucleus. An R42 value near 2, you know something about the nucleus. R4 value of 3.33, you know something about the nucleus. Measuring E2 plus doesn't tell you anything about the nucleus, because the energy formula is this. And you don't, unless you know what I is, E2 plus is not invariant over the nuclear chart. And that's why in the rare earth region, the best deformed nuclei have 2 plus energies around 80 kilovolts. In the actinides, they're around 45 kilovolts. But a nucleus with a similar shape in magnesium is 800 kilovolts. So some of you yesterday looked at magnesium-32 and saw that the 2 plus state was at 800 kilovolts. And you said, oh, that's high. It can't be deformed. Got to be careful. 2 plus energy, the absolute value of the 2 plus energy is not mass invariant. Okay, so, and that comes directly from this moment of inertia. Okay, quadrupole moments, they go as beta, and then a correction factor, which is usually pretty small. Typical values of beta are 0.3, as we'll see in a minute. And so 0.16 times 0.3 is 0.05, so that's pretty small. So the quadrupole moments are proportional to the elongation. And BE2 values from the first 2 plus state to the ground state, I'm not deriving this, I'm just telling you, go as the quadrupole moment squared, which means they go as the deformation squared in first order. And that, these two facts here allow us to deduce something very nice. But first, first let me, I want to look at these BE2 values just experimentally for a moment. So you've seen this plot already. They're very, very small for magic nuclei. They're very big for collective deformed nuclei between magic numbers near mid-shell. From these values, using this equation and this equation, we can actually experimentally extract beta. And so,
One question.
yeah.
The quadrupole moment, is it correct that it's linear in deformation because we have beta times, and in the brackets there's again beta, so it should be squared?
Well, this is going to be beta, and that's going to be beta times about 0.05. Beta is about 0.3.
Yeah.
So 0.3 times 0.16 is 0.05. compared to 1. So that's why I say in first order it's linear.
Oh, okay.
There are correction.
I
Yeah.
didn't get the
Yeah.
first order.
Okay.
Can I ask also something about the B2? Because
Yeah.
usually, somehow, I always think of quadruple moment as the diagonal matrix element. And so the quadruple moment of the ground state would be like the diagonal matrix element of the ground state. And it's kind of the B2. So going from the 2 plus state to the ground state depends only on what is the quadruple moment of the ground state. It doesn't tell us anything about the 2 plus state.
This formula assumes that the shape of the nucleus is not changing as you go from one state to another.
Yeah,
Okay.
because it's, it's a rich dropper. It's
Exactly,
rotating
yeah.
and, I think of it.
Okay? Okay. So what I want to do now is use this data here, this region, to actually extract values of beta. So I have this expression for the quadruple moment. I ignore that. The BE2 value is this formula which I gave you. The formula I showed you, it comes from this thing with a Clebsch-Gordon coefficient. And so from this and from this, I can get that the BE2 goes as beta squared, or beta goes as the square root of BE2. And so from the measured BE2 values, being careful about these constants, I can actually extract beta 2, or beta as I've called it. And you get, these are typical values that you get across the rare earth region. Okay? They're small at the edges near the closed shell. They go up to typically a little more than 0.3 in mid-shell. Okay? Notice they don't go to 0 at the closed shells. If I put lead on here, lead is a doubly magic nucleus. It would not be 0. And that has to do with 0-point motion, but we'll get to that later. Okay? Now, nuclei that are deformed, not only can they rotate, they can also vibrate. There's no reason why they can't vibrate. And so the levels of a deformed nucleus will consist of a ground state, vibrational states, and rotational sequences built on top of them. And we've seen that. You saw this already, but now I want to go... You saw a very simplified version of this, without this stuff, okay, and without some of the other stuff I'm going to put up here. Now I want to go into this in much more detail. So there's the ground state. Fortunately, nuclei have ground states. Here you have a set of rotational states. By now this should be very familiar to you. 0, 2, 4, 6, 8 that satisfy this formula, approximately. And what I've done here is I have fixed h bar squared over 2I to match the energy of this 2 plus state. So remember somebody, Justin, was asking, can you predict h bar omega? So it's the same thing here. In a collective model, you can't predict what h bar squared over 2I is going to be. Okay? You have to feed the model some information. So here I feed it some information by normalizing this. And then I predict these states. Okay? And
How close do you get if you just use that real crude I is proportional to 8 and the 5/3?
On a relative scale, let's say the moment the rotational spacing's in mass 100 compared to mass 150 compared to mass 230, you do okay. I don't actually know what on an absolute. I haven't calculated that.
That sounds like a good exercise.
It could be, yeah. We can add that in. You can do that one. Okay. Let's look at these numbers, the comparisons. What do you see if you compare these two sets of numbers? Is the agreement good or bad? Is it perfect? Okay.
Go higher in the excited state, then the experimental value is a little bit lower than the.
The experimental values are always lower than the theoretical. So, first of all, when you see this, what you should say, or what I think you should say, is this is remarkable agreement. I mean, think what we've done. We've got a nucleus with 150, how many? 164 particles. And all we've done is say it rotates, and we get these states to within a couple of percent. It's not too bad. Not too shabby. Does everybody know that expression in English? Not too shabby? It means good. Okay. Yeah? You have a question? Okay. Now, you see there's some differences, though. Okay, why?
I think if we stay in the same framework, so we can imagine, like, I think this model is sometimes called a liquid drop model. So when we rotate a faster liquid, this liquid gets maybe pushed a little bit outside. So the moment of inertia, so the m square ready grows a little. So the moment of inertia also grows. So the spectra also gets a little bit closer. So the effective moment of inertia rises. So that's why our real data is a little bit lower than the...
Okay, interesting answer. Yeah?
Could we add in some vibrational effects?
What do you mean by vibrational
Well,
effects?
right now we're just rotating, but as you said, rotors can also vibrate.
Okay, good. Other answers?
You're assuming rigidity, but that's not.
Is that different than what is it? I think somebody over here said something. I'm sorry? Just say it again, I didn't hear. You're agreeing? Okay. Okay, actually you're both right. The order of magnitude of the effects is a little bit different. Vasily, right?
Yeah.
His explanation was pretty much, okay. There are some people who are going to tell me it has to do with structure of pairing, but I'm going to ignore that. What you said basically is a centrifugal force.
Yeah, I say, let's say in the same model.
Yeah. As the nucleus rotates, if I go like this, or if I go faster, okay, I'm going to spread out. And so the radius will increase, the moment inertia will increase, and the energies will drop. Is that clear? Now, your comment about vibrations. So if you think about what that really means is, there are vibrational excitations. We're going to talk about them in a minute. And what your comment is equivalent to is saying that they can mix with the ground state, or with this ground state band, and that these states will have some admixture of these wave functions. They will be vibrating a little, right? And that's absolutely right. It turns out in practice that effect is typically less than a kilovolt. But the effect is definitely there. Okay, so the main reason is centrifugal stretching. Okay? All right. Now here we have vibrational excitations, which I already introduced this name because I wanted you to do that exercise. Okay, this is called a gamma band, and it corresponds... All right, stopping. This will be the last slide before the break. It corresponds to an oscillation like this. Okay? All right, and it has angular momentum 2. We'll talk in a minute about why it has angular momentum 2. And then it has a rotational band built on top of it, 3, 4, 5, 6, and so on. Here are the energies again, and I've normalized this spacing. And again, you see that these spacings are really quite well. There's something funny here, and I don't understand that. But typically they're lower. Maybe I wrote that down wrong. They're lower than the predicted ones. And then you have another excitation here, which has 0 angular momentum. I haven't introduced the K quantum number, but don't worry about that. And again, it has a rotational band built on top of it. This is sometimes called a beta vibration. And the idea of beta and gamma vibrations were introduced, as far as I know, by Bohr and Modelson. Bohr and Modelson also proved that beta vibrations can't exist. And so I hesitate to call them beta vibrations. And if you want me to go into why they can't exist, we can. But in any case, almost all deformed nuclei have a low-line state with angular momentum 0 and a rotational band built on top of it. And whether you call it a beta, I will tend to call it beta vibrations just because I grew up that way and I can't stop my mouth from saying it. But I'm not really implying a specific... A beta vibration would mean an elongation like this. Okay, but anyway, those are the states you get. And this gamma is squishing and beta is elongation. These are rotational, I already said that. These are rotational states built on that. And note that the wave functions of all of these states have both intrinsic and rotational parts. Okay? In other words, the ground state has a certain structure. These states are simply rotational motion superimposed on the ground state. This has a certain intrinsic structure, And these states are rotation superimposed on that. And the same thing here. By the way, in odd mass nuclei, it's much more subtle. And I don't, well, maybe I'll get into it in the third week. Depends if I have time. Okay, so they have an intrinsic part and a rotational part. That will be very, very important later on and relates to the exercise you did on Erbium 168. Okay, I think, okay, I will tantalize you with this coming up, and let's stop here. Okay, let's have a